The curve that barely moves. In this animation, we will look at 4 mathematical functions and watch what happens to each of them as n grows very, very large. The contrast between them is the entire lesson. Here are our axes. The horizontal axis represents n, the size of our input, growing from 10 all the way to 1 billion. The vertical axis shows the number of operations on a logarithmic scale, so we can fit all 4 curves on the same chart. Let us now draw each function and see what shape it takes. First, n squared. On this log scale, n squared appears as a straight line with a steep slope. Notice how it shoots upward and completely flies off our chart before n even reaches 100,000. At 1 billion, n squared would require more operations than there are grains of sand on Earth. This is not an algorithm we can run at any meaningful scale. Next, linear growth, or order n. When n doubles, the operations double with it. On our log scale, this appears as a clean diagonal line. It climbs all the way to the top of our chart at 1 billion, meaning 1 billion operations. At a modern processor speed, that is roughly 1 full second of waiting. Better than n squared, but still not great when n is very large. Now, square root of n. On our log scale, this is also a straight line, but with exactly half the slope of the n curve. At 1 billion, the square root is about 31,000 operations. Much more manageable. The curve rises gently, reaching only halfway up our chart. This is considerably better, but we can do something that seems almost impossible by comparison. And now, log n, watch this very carefully. It rises at first, yes. But then it begins to flatten. And flatten. And flatten some more. By the time n reaches 1 million, the curve has almost completely stopped rising. While every other function climbed to impressive heights, log n is hugging the bottom of our chart. This is the function that changes everything about how we design algorithms. Let us now mark the point where n equals 1 billion and read off what each function says. N squared left the chart long before reaching 1 billion. At this scale, it would need more than 10 to the power of 18 operations. Completely unusable. Linear n needs 1 billion operations. At 1 GHz, that is roughly 1 full second. Square root of n needs about 31,000 operations. Already much, much better. And log base 2 of n. 30. Just 30 steps. To search through 1 billion records. That is not an approximation. Log 2 of 1 billion is exactly 29.9. We round up to 30. That is the power of a logarithm. This is why logarithms appear everywhere in computer science. Not because mathematicians placed them there deliberately, but because every time an algorithm can cut the problem in half at each step, a logarithm appears naturally in the step count. Binary search. Balanced trees. Merge sort. All of them are just different ways of asking the same question, which half? And that question, repeated, is a logarithm. The curve that barely moves.